Hey everyone, welcome back to Calculus 1. This is going to be lecture 15 of the series. So in the previous lectures we've discussed extrema on an interval, and we've discussed the mean value theorem, and a handful of other things that are getting us closer to our quest, closer and further along in our quest to being able to sketch curves efficiently using calculus. And so what we're going to discuss today is called the first derivative test, and it's going to give us a lot of it's going to increase our ability to efficiently plot functions and to understand not just drawing functions, but also being able to reason about them intelligently and without having to plot points or resort to graphing utilities. So we'll call this section 3.3, and this will be the first derivative test. Okay, so this is going to take, basically what we're doing here with this first one is we're basically just going to consolidate a lot of information that we already have. We're going to kind of consolidate some stuff and see how we can apply it, a range of ideas to the solution of a particular type of problem. So let's start with a definition. So a function f is increasing on an interval if, now here's the thing, so if for any two x1 and x2 in the interval, so a function f is increasing on an interval if for any two x1 or an x2 in the interval, f of x1 is less than f of x2 whenever x1 is greater or is less than x2. Okay, so so this is very straightforward definition, right? So if I have a function, right, and it's increasing, let's say I've got an interval here of interest, right? So it's going to be that range there. If this is x1 and that is x2, then it better be the case that f of x1 is less than f of x2 on that interval, right? So here's x1, here's x2. Okay, and so you can see on an interval where the function is strictly increasing, that's going to be true for all x's in there, isn't it? So any 2 points that I pick between here and here, really on the whole graph of what I've drawn here, but any 2 points certainly in this range, if x1 is less than x2, then f of x1 is going to be less than f of x2. Okay, so that's the idea with increasing functions. So we can just extend this for the decreasing case, right? And so what we would say, f is decreasing on the interval, on interval, if for any two x1, x2 in the interval, f of x1 is greater than f of x2 whenever x1 is less than x2, right? So x1 and x2 are going to have the same relationship in both cases, both of these cases, but the f of x1 and the f of x2 are going to be the reverse, right? So in the case of a decreasing function, let's say we're interested in this interval here, from there to there. Here's your x1, there's your x2, right? And so you're going to have f of x2 and f of x1, right? So here you can see that, sorry about that, when x1 is less than x2, then f of x1 needs to be greater than f of x2, right? And that's the relationship. Here's f of x1, here's f of x2, right? x1 and x2 have the same relationship as they did above, but the values of the functions at those 2 points are different, are reversed. Okay, so super straightforward definition, I think. Like this should square with everybody's intuition of what an increasing or decreasing function would be. Okay. So with that, let's move into our first theorem here. And this one is going to be, let f be a function, okay, that is continuous on AB, so an interval, closed interval AB, and differentiable on the open interval AB, right? So so it's differentiable everywhere in the interval except at the endpoints. Okay, so then there's going to be three statements here. So the first statement is, if f prime of x is greater than 0 for all x in AB, right, the open interval AB, then f is increasing. On AB. Well, that should be closed interval AB, I think, right? So, okay. So that's the first thing. So if the derivative is positive for all x in the interval AB, then the function is increasing on that interval, right? So that's just by definition of sort of what the derivative tells us, right? The derivative kind of tells us the slope of the tangent line of the graph at any point. So if the slope of the tangent line of the graph is positive for every point in the interval AB, then the function is increasing on that interval. Okay, so that's the first thing. The second thing will naturally be the less than statement, right? So if the derivative evaluated at x is less than 0 for all x in AB, then f is decreasing on AB, right? Makes sense, right? So it's just a reverse statement. This means the slope of the tangent line of the graph is negative at every point in AB. So naturally the function itself will be decreasing according to this definition up above. Okay. And then notice here that this is strictly greater than, this is strictly less than. So what happens in the equality case? Well, if the derivative is equal to 0 for all x in AB, then f is constant on AB. Okay, so those are all very intuitive ideas, hopefully. So as I said at the onset, we're kind of consolidate a bunch of things that we've already talked about. So we've definitely talked about what does it mean when the derivative is negative, what does it mean when the derivative is positive, and what does it mean when it's 0, right? And so all we're doing is kind of extending that idea to be able to talk about functions increasing, functions decreasing, or functions being constant, right, based on the values of the derivatives. Okay. Excellent. Let's go ahead and prove this theorem. Okay, so we won't prove all three of them. We'll just prove the first one because I think the others are very similar. I mean, basically identical. So we'll kind of take this in cases. So we'll just prove the first part of the theorem. So we'll prove 1. And so to prove 1, okay, assume f prime of x is greater than 0 for all x in the open interval AB. Okay, so we're assuming that the derivative is positive for all of the x values in some interval AB, and let's let x1 be less than x2. Okay, and these let x1 be less than 2 be any points in the open interval AB. Okay, so those are just, if you recall, those are the basic assumptions of theorem, right? So let's double check that, just to make sure we're clear on that. So f is a function that is continuous on AB and differentiable on AB. So the assumptions are that f is continuous and differentiable, and we're assuming that derivative is greater than 0 for all x in AB, right? And so that is an assumption that we're making. We're also assuming, we're going to pull this definition into place, and we're going to assume that x1 and x2 are two values in the interval, and that x1 is strictly less than x2. Right? So those are all of the assumptions that we're going to make here. Okay, so to prove statement 1, we assume that the derivative is positive for all x in the open interval, and we're going to let x1 be less than x2 be any 2 points in AB. Okay, so then by the mean value theorem, right, so we're going to pull this in. Okay, by the mean value theorem, there exists a C such that x1 less than C is less than x2. Okay, so right, so this is just a fact of analysis. If you have 2 points and they are definitely not, if you've identified 2 points on the real number line, they are not directly adjacent to one another. There's always going to be some third point in between them. Okay, so this is just a fact of the real number system. Really, kind of, we're taking this for granted here. Right? If you get into a more rigorous calculus course like real analysis, then this would be like something you'd have to justify. But we're going to take this for granted that there's always going to be a real number between any two other real numbers. And so the mean value says that there exists C such that C is between x1 and x2, and the derivative evaluated at C is equal to f of x2 minus f of x1 divided by x2 minus x1. Okay, so remember, this is the mean value theorem. If you need to, pause the video and go review that. But basically, the slope of the derivative of the tangent line is going to be equal to the secant line formed by these two endpoints. Right, so that's the idea with the mean value theorem. Right, and we just basically are going to use this as machinery to prove this theorem. Now, so this is all mean value theorem. This is an assumption of real analysis that we take for granted here. Because f prime of C is greater than 0, right? And x2 minus x1 is clearly greater than 0, right? x2 is larger than x1. It follows, right? What follows? It follows that f of x2 minus f of x1 is greater than 0 as well. Now, why does that follow? Well, if you look at this expression, right, so we're saying this is greater than 0, and we know that this is greater than 0, right? So this is kind of just, by, just basic like arithmetic will tell you that if this is a positive number, this is a positive number, then this can't be a negative number, right? This has to be a positive number as well, right? So because this side is positive, the denominator is positive, it follows that the numerator must be positive as well. Okay, and so what does that imply? Well, that's the result, isn't it? That implies that f of x2 is greater than f of x1, and that's just algebra, right? And what does that mean? Well, this is the definition, right? So f is increasing on the interval. All right, so that's a very nice, simple proof, right? It's got very simple moves. There's nothing that's too that requires too out there of thinking. It's very straightforward, hopefully, right? So it's basically, there's a lot of assumptions here. Make sure that the assumptions all make sense, right? So the derivative has got to be positive for everything in the interval, right? That's a big assumption, right? So you'd have to know somehow that that's the case, right? But, if you can justify that, and you have an x1 and x2 that, where x1 is less than x2, and these are arbitrarily chosen from the interval, okay? Well, then the mean value theorem says that this is true, and then basic logic tells you that this numerator must be positive, which implies that f of x2 is greater than f of x1. So very basic logic. Okay, now to prove 2 and 3, you can use very similar logic. Okay, so we'll call that the end of the proof for now. And it's, again, I mean, you can go and kind of verify 2 and 3. 2 is almost identical to this, just basically flip some of these assumptions, right? So here, in the case of 2, this would be assumed to be less than 0, right? This would be assumed to be greater than 0, and so that's going to imply something about this, namely that this is less than 0, right? So it's almost exactly the same moves. You know, the inequalities would be a little bit different, but that's simple, easy to negotiate. Okay, and in the case 3, again, also very similar. Excellent. Okay, so let's see an example where we can use this theorem and see what it can tell us. Okay, so example. Let's start with this function, f of x equals x cubed minus 3/2 x squared. Okay, so given this function, we want to find the open intervals on which it is increasing or decreasing. So find the open intervals on which f is increasing or decreasing. Okay, and obviously we kind of want to do this without plotting anything, right? We don't have to plot anything. So let's find the derivative first, right? Let's start with the derivative. This will also be a good review of kind of what we've talked about in previous lectures. So let's find the derivative here. So f prime of x. Can we differentiate this function? You betcha, right? So this would be 3x squared, and then it's going to be minus 3/2, and then it's 2x, right? Differentiating this part. And we can clean that up a little bit, and this would be 3x squared minus 3x. We could probably leave it like that. All right. So we've got the derivative. Now, one of the things we're going to rely on is we want to know where the critical numbers, critical values are for f, right? And so what does that mean? If you recall, that's going to be where we have relative maxes and relative mins, and those are found. So I'll write it, critical values. I think numbers might be better. Let's write critical numbers can be found by solving f prime of x equals 0. So we got to solve the derivative, set the derivative equal to 0, and solve for x. And so in this case, it's super easy to do. So we would say 3x squared minus 3x equals 0, and that's going to imply, right? So it's factor out the 3x, and you have x minus 1 equals 0. Right, so we've got a couple of zeros here. So the first one is found by setting 3x equal to 0, so that implies x equals 0. Oops. Okay, so that's one of the critical values. The other one is found by setting x minus 1 equal to 0, so that implies that x equals 1 is another critical value. Okay, so you've got the two. Right, and this is the derivative is a quadratic function, so we shouldn't expect there to be more. There's just the two. Great. Okay. All right. Very good. Let's. So what can we do with this information? Well, so basically, if you think about this, so you've got x equals 0 and x equals 1 are critical values. Okay, and so you can kind of think like, if I have a number line here and say this is x equals 0, and we'll say this is x equals 1. All right, those are my two critical values. So there's going to be something happening here, right? There's going to be something going on here with the function, like i.e. it's going to be increasing, decreasing, one of the two. There's something happening here with the function as well. It's going to be increasing, decreasing, one of the two. We don't really know what yet. And then there's going to be something happening here as well, right? Increasing or decreasing. Okay, so we don't know which is which and what's happening in these intervals yet. All right, so it's increasing or decreasing. So, but then what do we know is happening at these 2 points? What we know is happening at those 2 points is we know that the derivative is 0. That means the function is flat at those 2 points. So it could be that what's happening is the function is coming up and then hitting a 0, a relative max, and then it comes back down, and then it hits maybe another 0 here, and then maybe it goes back up, right? That's one thing that could be happening. It could be doing the reverse too, right? It could come down, you know, reach some minimum, and then come back up, reach some maximum, and then go back down. It could be doing that too. We don't know. It could be doing this. It could be doing that. It could also be doing something like this, where it kind of comes down, hits like a flat point, and then goes down further, right, and then comes back up. It could be doing, you know, any number of things. But what we know for sure is that we have relative mins or maxes, or potentially this kind of inflection point change here for these at these points, okay? And what we need to do is figure out what's actually going on in the intervals, okay? So what I like to do is, I mean, and this is like kind of how most people do this, is kind of define these regions. So you got x less than 0, right, this part here. Then you're going to have x between 0 and 1. That's kind of here. Okay, and then you're going to have everything that's where x is greater than 1. Okay, so x greater than 1. Yeah, so those are kind of the regions of interest. So what's happening with the derivative in these points? That's kind of our question. And so what we can do is we can just pull out the first derivative here, and let's test a point. So we let x equal -1, for example, here. Okay, so if I plug in f prime of -1, what do I get? Well, let's do that. You would plug it into 3x squared minus 3x, so that'd be 3 -1 squared minus 3 times -1. And you'd get, let's see here, you'd get about 6, right? So this would be 3 plus 3, so 6. That's positive. So it's greater than 0. What does that mean? Well, that means on this interval here, the derivative is positive. So f prime of -1 is greater than 0, means it's increasing in that region. What about in this section here? Well, let's find a nice x between 0 and 1. I guess the best we can do is probably like x equals 1/2. So f prime of 1/2, okay, and again, kind of plugging in all these quantities, 3 times 1/2 squared minus 3 times 1/2. Right, when you do all of that and you crank through all of these numbers, here you get 3/4 minus 3/2. Let's see, hold on. I think you get -3/4 here, don't you? Yep. So -3/4, so that's less than 0. Okay, so the derivative, f prime of 1/2, is less than 0 here. And so that means it's decreasing, doesn't it? Makes sense. So it's coming up to this point here, and then it's going to drop back down. So so far it's kind of looking like this is the scenario, the first scenario that we sketched out. And then let's just test something above x equals 1. So maybe we can just use x equals 2. So f prime of 2. So that's 3 times 2 squared minus 3 times 2. It's getting a little small over here, but you can see. And then when we plug all of that in, we should get 3 times 4 is 12 minus 6, so 6, greater than 0 again. So f prime of 2 is greater than 0, so here it's increasing. All right. Increasing, decreasing, increasing. Okay, so it is, in fact, this kind of a scenario. Okay, let's plot this actual function here and see what this looks like. I've gone ahead and done that ahead of time, so I know what it looks like to make it a little easier for us. So here's our 0, 0. So f of 0 is 0, right? And so you've got the 0, 0 point here. And then you've got, so we'll put this as 1. And so 1, 2, 3, 4, 1, 2, 3, 4. And this will be -1. And so then if you plug 1 into the function, remember the function is f of x equals x cubed minus 3/2 x squared. So if you plug in a -1 here, then what do you get? You get, let's see, f of -1, I guess. We can just calculate it quick. So you'd get a -1 minus 3/2. So that would be -2/2 minus 3/2, so -5/2. All right, so it's somewhere down here. So a little bit greater than 1. So it's somewhere right approximately here. You would have 1 comma -5/2. Okay, and so what's happening with the function? Well, we don't know a lot about, you know, the actual like slopes, but what we do know is that it comes up to here, and then it turns around, it comes back down to here, okay, and then it turns back around again and goes back up. We have no idea like what happens after that, but we know that these intervals are as described. Okay, and so remember, our initial question was to find the open intervals on which f is increasing or decreasing. Okay, and so we can answer that question now. We can say that f is increasing on, right, and I guess what we would say is -infinity up to 0, and then it's increasing here as well. So from 1 to +infinity, f is increasing on those two intervals, and f is decreasing on 0 up to 1. Okay, so it's decreasing here from here to here, 0 to 1. It's increasing everywhere over here, and it's increasing everywhere past 1 as well. Okay, so that's the idea here. Okay, now notice we had this information before we plotted it. Basically, the information is here, right? We know that it's increasing everywhere x is less than 0. It's also increasing everywhere x is greater than 1, and it's decreasing in that 0 to 1 interval right in the middle. Okay? Excellent. Okay. All right. So let's see here. So so that gets us really close to the first derivative test. So let's go ahead and describe that theorem next. So the first derivative test. Okay. Let me make sure this is focused properly. Okay. So the first derivative test. So let's see. Here's what it says. So let's see be a critical number of a function f. So let C be a critical number of a function f that is continuous on an open interval I containing C. Okay, so this is the first windup. Right, so let C be a critical number of a function f, you know, and f is continuous on an open interval I that contains C. Okay. If f is differentiable on I, okay, except, you know, possibly at C. Okay, then f of C can be classified as follows. Okay, so let C be a critical number of a function f that is continuous on an open interval I containing C. If f is differentiable on I, except possibly at C, then f of c can be classified as follows, right? So two cases here, two classifications. If f prime of x changes from negative to positive at c, then f of c is a relative minimum of f. Okay, all right, very good. So if f prime of x changes from negative to positive at c, then f of c is a relative min of f. And if the reverse is true, if f prime of x changes from positive to negative at c, then f of c is a relative max of f. Okay. All right. Okay. So, probably that is coming through as clear. But let's draw some pictures to make sure this makes sense. So visually, what do we mean here? Well, so let's say we've got, here's our a, here's our c, and our function is kind of doing something like this, right? And then our c point is just kind of here in the middle. Oh, this should be a b. I'm gonna try b there. Okay, so c is here in the middle. Right, now what's going on here, right? So on this side, f prime of x is going to be less than 0, right? On this side, f prime of x is going to be greater than 0. Now, what do we mean by that? Well, if you imagine a tangent line here, the slope of that tangent line is negative. Or sorry, the slope of this tangent line is positive, right? So it's heading up, right? If I have a tangent line on this side, the slope of that tangent line has to be negative, right? Okay. Slopes are negative, slopes are positive, right? And so if that's the case, then what's right in the middle? Well, remember, c is a critical number of f, right? So it is naturally going to, in this case, be a minimum. So what happens in the case of, right, the reverse, right? Well, if you have something that looks more like this, right, and maybe your c is right in the middle, right? So in that case, all tangent lines to this side are going to be positive. All tangent lines on this side will be negative. So the derivative over here is greater than 0. The derivative over here is less than 0. Slopes are positive. Slopes are negative. Okay, right? So it's hopefully that's intuitive, right? And so basically, if your slopes are all negative and then they suddenly hit 0 and then they all become positive, it should be obvious that that means that you have a relative minimum. Okay. Now, what else can happen? Well, technically, other things can occur. Let's see what those look like. All right, so you could have something like this, where you've got your A and your B and your C right in the middle, and maybe the graph comes up, flattens out, and then, as we said, kind of heads up, continues to head up. All right, so in this case, you've got 0 here, but over here f prime of x is greater than 0, and over here f prime of x is also greater than 0. Right, so what does that mean? Well, it means you don't have a relative maximum or a minimum. So in this case, no relative max or relative min. Right? So this is what we talked about last time, right? Or in the previous example, I kind of sketched out 3 scenarios. I said it could go in like this, it could go like this, right? It could do one. It could come up, go down, go back up. It could come down, go up, go back down. I also said it would be possible for it to go like this or like this. Sorry about that. Right, so it could come down for a bit, flatten out, and then go back down, or it could be coming up, flatten out, go back up. Right, so in these cases, you have relative max and mins. In these cases, you do not. And that's what the first derivative test is telling us. It's saying, hey, if you've got a critical value, all you got to do is test the derivative on either side to figure out if it's a max or a min, or neither. Right, and then so like just to round this out, the last thing that can happen would be, you know, the graph kind of comes down, flattens out, and then goes back down more. Right, so this is not a relative max or a relative min. It's just, you know, kind of in the middle. Okay, so no relative max or min here. Okay. All right, very good. Let's do a couple of examples here where we explicitly rely on the first derivative test. So, example. Find the relative extrema of the function f of x equals 1/2 x minus sine of x on the interval. All right, and the interval is going to be 0 to 2 pi. Okay, so can we find the relative max and min, if there are any, for this function on this interval from 0 to 2 pi? Without graphing. We're not going to graph anything. Well, let's differentiate it. That's definitely going to be the first thing we need. All right, so we can differentiate this really easily. This is d dx of 1/2 x minus sine of x. And so differentiating that, you get 1/2 minus, now what's the derivative of sine? It's cos. Okay, just like that. 1/2 minus cosine of x. Okay. Now let's find the critical numbers. And so set f prime of x equal to 0. And so when we do that, we have 1/2 minus cos x equals 0. Okay, and from that, it's pretty easy for us to say that cos x equals, well, negative cos x would equal negative 1/2, right? Just doing some algebra here. And then cos x equals 1/2. Okay, and so if you kind of remember back to your trigonometric equations, what the goal here is then to find some angle, in this case x, where the cosine is 1/2, and we have to observe that we're operating on the interval 0 to 2 pi. And so there are 2 such values of x. This is a nice, 1/2 is a nice number, so we do have x equals pi over 3, or x equals 5 pi over 3. And so you could pull out a unit circle and kind of think this through, if you want to. You can also use the inverse cosine function of a calculator, but so basically what this is going to say is that at pi over 3, which is roughly in the middle here, right, then the cosine is 1/2. Okay, that's pi over 3. And then the other time this happens is let's see, so it would be over here, right? So it'd be basically the same thing here. Now, in this case, theta is just up to this line, but in the case of this other side, theta would have to go all the way around, so that's where you get 5 pi over 3. Sorry, this is very tiny, and basically here you'd have the same, oh, wait a second. I think that's right, isn't it? Yeah, okay. Right, so you'd still have 1/2 there. Okay, so the critical numbers then, right, are the solutions to the equation you give when you set the derivative equal to 0. So the critical numbers are x equals pi over 3 and x equals 5 pi over 3. Okay. All right. Oh, actually, I'm sorry. I'm in the wrong quadrant here. I was looking at this like, no, something's wrong here. So I should be down here as well, right? So here's the half, right? So this should come all the way around. I apologize. That's the 5 pi over 3, so ignore that part. Boy, that's very messy and probably just confusing people more. So yeah, so you've got pi over 3 here, and then 5 pi over 3 would be all the way around here, right? And then you'd have only one more third of a pi until you had reached 2 pi, which would be the entire revolution. Okay, but so review that on your own. This is terribly messy, but basically, like, you know, you've got two solutions to this equation, this trig equation, and they're pi over 3 and 5 pi over 3, right? So two solutions within this interval anyways, this interval 0 to 2 pi. Okay, so then we're just going to use the first derivative test. We were looking for relative extrema, so you've basically got three intervals to be interested in here. You got 0, less than x, less than pi over 3. Okay, so that's from here to here, basically. And then you've got from pi over 3 up to 5 pi over 3, so that's from here all the way around. And then the last piece of it would be from here up to 2 pi. So from 5 pi over 3 up to 2 pi. So in this case, you do have like upper and lower bounds on the range, on the interval that you're interested between 0 and 2 pi. Right, so you've got these three intervals to consider. So then all you really need to do is just test values in there and make some determinations about whether x equals pi over 3 and x equals 5 pi over 3 are relative maximums or minimums or neither. All right, so we're going to test a value here. So let's test an x in this range. Well, a good one to test would be x equals pi over 4. Right, and so f prime of pi over 4, that's going to be equal to, let's see, so it's 1/2 minus cos of pi over 4. Okay, and what do you get? Well, cosine of pi over 4 is, let's see, so that's going to be when you're like right about here. That one should be a little higher. So pi over 4. So I think it's going to be 1/2, right? So 1/2 minus 1/2. Okay. No, that's not right. Square root of 3 over 2. Oh, I'd have to look it up. Shoot. I'd have to look it up. I don't have it written down. So it'd be equal to 1/2 minus, I think it's square root of 3 over 2. Okay, I'm going to have to double check that. But at any rate, you're going to get something less than 0 here. Okay. All right, and so that means the derivative f prime of x is less than 0 on this interval. And then what happens in between here? Well, let's just test the value x equals pi. And again, I apologize. You'll have to pull out. I don't have my calculator handy, so I can't confirm these values. But if you test the derivatives here, so f prime of pi, right? Again, that'd be 1/2 minus the cosine of pi. So cosine of pi is 0. Yeah. So what you'd end up with here is the derivative is 1/2 minus pi, or 1/2 minus 0 would be greater than 0, right? So it equals to 1/2. And so you've got the derivative is increasing here, and it's decreasing here. That sounds to me like a relative minimum at pi over 3. And then up here, we got to test a value in this range, and so we can test something like maybe 7 pi over 4. That would work. All right, so that's not quite 2 pi, but it's larger than 5 pi over 3. And so the derivative there is going to be, if you plug that into a calculator, you'll see that it's less than 0. Okay. Okay, and so if you, let's think about this interval here. clean this up a little bit better. So 0 less than x less than pi over 3, pi over 3 less than x less than 5 pi over 3, and 5 pi over 3 less than x less than 2 pi. Okay, so in those three intervals. So here the derivative is less than 0, here the derivative is greater than 0, and here the derivative is also less than 0. Right? So it's, what is it doing? It's decreasing here, it's increasing here, and it's decreasing there. Right? So what does that imply? Well, f has a relative max at x equals pi over 3 and a relative min at x equals 5 pi over 3. Right? And so this is the first derivative theorem. Okay, let me pull that back up here just real quickly. All right, so the first derivative theorem says that if f changes from negative to positive, then you have a relative minimum, right? So if f goes from negative to positive, then you have a relative minimum. These are exactly backwards. There we go. So f has a relative minimum at x equals pi over 3 because it goes from negative to positive. Okay. And then the second piece of the first derivative test says that if the derivative changes from positive to negative, then you get a relative max. Right? So here it was positive and it became negative, and so you're going to have a relative max at 5 pi over 3. Okay? Does that make sense? Hopefully. I know I've got a little careless with my trigonometry here, but hopefully that's you can just pause the video and confirm those values. But I think this is all correct now. So 5 pi over 3 looks like this, and the derivatives are indeed this. I forget what the exact values are of these things. I don't have a unit circle in front of me, but you can confirm all of that. The big point here is that you calculate the values of the derivatives at some test value in the interval, and the pattern of going from decreasing to increasing is going to imply a minimum, and going from increasing to decreasing is going to imply a maximum, right? So you're coming up to a max, here you're coming down to a min. Okay. All right, let's do one more example. Let's see if this, just to kind of drive this home. So again, want to find the relative extrema. Of f of x equals x squared minus 4 and 2/3 power. Okay, so in this case, we're talking about there's no interval given, right? So the assumption that we should make here is that we're talking about the entire real number line. Okay, so find the relative extrema of this function basically on all of R. Okay. And so, the assumptions for the first derivative test need to be that this is continuous and differentiable, and that's fine. That is true, right? So we have continuity and differentiability here, so no problems there. So let's find the derivative. Start with that. F prime of x equals, and then this is going to be a chain rule issue, right? Because we've got a function inside of a function. And so we'll differentiate the outside first, and so we get 2/3 x squared minus 4, and then it'd be 2/3 minus 1, which would leave you with a negative 1/3. Okay, and then we need to differentiate the inside, so instead of x squared minus 4, when we differentiate that, we get 2x. Okay, and so that's what the derivative kind of looks like, but we can clean this up a lot. So multiply the 2's together, and you get a 4x, and then down below it would be 3 and then the 1/3 power of this thing. So 3 x squared minus 4 to the 1/3 power, like that. Okay, so that is our derivative. Now, one thing to notice is that we do have a denominator now with a variable in the denominator, so we're going to have some possible domain questions here for the derivative. And basically, we can see that anytime this derivative is equal to 0, or sorry, this denominator is equal to 0, then the derivative is undefined. So f prime is undefined whenever 3 times x squared minus 4 to the 1/3 power equals 0, right? And so you could take a second here to figure this out. This looks way more complicated than it is. Divide both sides by 3 and then cube both sides would get you, basically get rid of the 3 and the 1/3 power, and you would get something that looks like this, right? And then that's a simple x squared equals 4 implies x equals plus or minus 2. So f prime is undefined at x equals 2 and x equals -2. Okay, so just things to know, right? So if the derivative is undefined, that means you have critical numbers there as well, right? So these are critical numbers in addition to whatever other critical numbers we might find. And so the other critical numbers to be found would be, you could identify by setting the entire derivative equal to 0. And so f prime of x equals 0 implies 4x over this whole thing equals 0. And again, this looks much scarier than it is. Let's just multiply both sides by 3 times quantity x squared minus 4 to the 1/3 power. And so when you do that, when you multiply both sides by that, you just get 4x equals 0. And so that implies x equals 0 is a critical value as well. Okay, so you've got 3 critical values here. All right, so this function is more interesting than the previous functions in the sense that, or than the previous examples, in the sense that we just have more critical numbers to be worried about. And whenever you have more critical numbers, you're going to have more intervals. Right? So in this case, we got 3 critical numbers, and that means we have 4 intervals. So let's write these down. I'll try to be very clean here. So x less than -2, that's our first bit. And then we've got wherever x is between -2 and 0. That's our second one. And then we've got 0 up to 2. Right, 0 up to 2. That's the third one. And then the upper interval is anything greater than 2. Okay, so we've got these 4 intervals that we need to figure out, right? So you could have a relative maximum here, here, or here. Those are the only 3 options. And to figure that out, we just need to know, is it increasing, decreasing, decreasing, increasing, decreasing? You know, you got to figure out what's happening on these intervals. And so basically just go through and pick some test values. X equals -3 is a good one. X equals -1 would be a good one. X equals +1, and x equals 3. Okay, and then just plug these values into the original function up here. Right, so that's the function. So basically just plug in those values successively in for x, figure out whether the, oh, sorry, don't plug them into that one. This is the original function. You want to plug them into the derivative, right? To plug them into this function here to determine whether the derivative is positive, negative, or 0. Okay, and so what happens when we do this? Well, f prime of -3, when you plug that in, you'll see that it is less than 0. Okay, so we're decreasing here. And when you plug in -1 into the derivative, you'll see that it is increasing there. And when you plug in x equals 1, you get f prime of 1 is less than 0. Decreasing there as well. Again, I went ahead and did these ahead of time, just in the interest of time. And then f prime of 3 is greater than 0. Okay, so you're increasing here. All right, so what's happening? Well, So what do we have here, here, and here? So here, because we're going from decreasing to increase, that means it comes down and then goes up. This is a min. Okay, and then here it's going up, up through this interval, and then down on this interval. So that means you're going to have a max here. And then here it's heading down, and then it hits a 0, and then it heads back up. Okay, that's the idea. Okay, so let's look at look like the graph. What does a graph look like? And I'll just kind of sketch it in here so you can see. Here's my x-axis. Here's my y-axis, and we'll say 1, 2, -1, -2, and then 0, 0 up at what, about 2.5? About here. So it comes down. So sorry. So it comes down there. Right, we know it's decreasing here, and it's increasing here, decreasing here, increasing here. Now actually what it does is it's nice and smooth here, and then these are like hard stops there. It's kind of, it basically it's not differentiable at these 2 points, at -2 and +2, and so you get this kind of W shape. Okay, and so the function is increasing on the intervals. What intervals? Well, the interval -2 to 0 and 2, infinity. And the function is decreasing on -infinity to -2 and on 0 up to 2. Okay, and then you've got min at x equals -2 and x equals +2, and a max at x equals 0. There we go. So that's the problem was really just asking for this last piece here, right? But in finding that, of course, you've identified the regions of increase and decrease. Okay, all right. So that is the first derivative test, and next time we'll get into the second derivative test. There's only 2. But then with that, we'll be in a really great place to start doing curve sketching. So we'll be able to find, what's happening on intervals, where the relative mins, maxes, where's, kind of the other things that can happen, and all of, we'll also be able to find inflection points and all of this kind of stuff as well. So until then, take care.